Welcome back to UST 107. This week we are covering weather. This is a fairly short chapter, so I'm going to try to do this all in one video. What we'll be covering is wind, air masses and fronts, atmospheric stability, visibility in clouds, thunderstorms, icing, fog, density, altitude, weather briefing, weather reports, forecasts, and charts, which covers surface aviation weather observations, aviation weather reports, aviation forecasts, convective significant meteorological information. So all of the weather on Earth begins with the sun. Energy moves outward from the sun's core through the radiative zone, eventually reaching the surface and radiating into space. The energy drives the solar wind and contributes to the sun's magnetic field, forming a vast protective bubble called the heliosphere, which surrounds the entire solar system. With the inner solar system, the terrestrial planets, Mercury, Venus, Earth, and Mars, orbit in close proximity to the Sun, exposed to higher temperature and stronger solar winds. These planets are more directly impacted by solar flares, coronal mass ejections, and radiation pressure. Earth's thick atmosphere absorbs incoming solar radiation, some of which is trapped by greenhouse gases, warming the planet through the greenhouse effect. The side of Earth facing the sun receives the most intense radiation, with the equator, due to its curvature and consistent solar angle, experiencing the highest average temperatures. The heating of Earth's surface and its surrounding air is uneven across the planet due to the angle at which sunlight strikes the surface. Near the equator, solar rays hit more directly, concentrating energy over a smaller area and producing greater heating. In contrast, sunlight reaching regions farther north and south spreads over larger surface areas, reducing the intensity of radiation and resulting in cooler temperature. Warmer air in the atmosphere tends to rise, being replaced by colder air that falls or settles, creating a large air cell circulation pattern known as wind. The unequal heating that causes pressure variations also cause variations in barometric altimeter settings between weather reporting points. Different surfaces radiate heat in varying amounts, creating a small area of local circulation called convective currents, which can cause turbulent air that may affect the remote PIC's ability to control the aircraft at lower altitudes. Areas with plowed ground, sand, rocks, and buildings give off large amounts of heat, which likely result in updrafts. Areas with water, trees, and other vegetation absorb and retain heat and are likely to result in downdrafts. Wind blowing against buildings creates strong updrafts that result in ballooning or a loss of positive control. Winds blowing over a building from the opposite side create downdrafts that have a dramatic sinking effect on unmanned aircraft. Air masses and fronts. When a body of air comes to rest on or moves slowly over an extensive area having fairly uniform properties of temperature and moisture, the air takes on these properties. The area which the air mass acquires its identifying distribution of temperature and moisture is its source region. As the air moves from its source region, it tends to take on the properties of the new underlying surface. The tend toward change is called air mass modification. When an air mass that is different in such properties advances upon a dissimilar air mass, the division line is referred to as a front. Remote PICs should always be aware of ambient and approaching weather systems, as they can significantly impact their operations and safety of flight. A ridge is an elongated area of high pressure. A trough is an elongated area of low pressure. All fronts lie in troughs. A cold front is the leading edge of an advancing air mass. They are usually accompanied by poor weather ahead of the front, which passes relatively quickly. There is a wind shift after a front passes due to the increased wind speeds. Turbulence is common for a period. More severe cold fronts can produce thunderstorms, hail, and tornadoes. Warm front is the leading edge of an advancing warm air mass. They move about half as fast as cold fronts and have more widespread impact on weather, often preceded by lower ceilings, increased precipitation, and reduced visibility. Frontal waves and cyclones usually form in slower moving cold fronts or stationary fronts. These types of systems are often accompanied by conditions that are not suitable for SUAS operations. And here I include a color legend of the weather map symbols. Atmospheric stability refers to how likely air is to rise or sink. Stable air resists vertical motion, which unstable air encourages it. This directly affects cloud formation, turbulence, and flight conditions. Stable atmosphere is air parcels resist rising. Clouds are typically flat and layered. Flying conditions are generally smooth. Unstable atmosphere, air parcels rise easily. This leads to vertical cloud development and turbulence. Visibility is the greatest horizontal distance at which prominent objects can be seen and identified. Flight visibility, what the pilot sees from the cockpit. Ground visibility, reported by observers at the airport. Prevailing visibility, most common visibility across the horizon. Clouds are formed by rising air cooling to its dew point, causing condensation. Classifications: high level, cirrus, cirrostratus, cirrocumulus. Mid-level, altostratus, altocumulus. Low-level, stratus, stratocumulus, and nimbostratus. Vertical development, cumulus and cumulonimbus. Stratus clouds are low-level, uniform clouds that often cover the sky in a gray or white layer, typically associated with overcast weather and light precipitation. Comes with low visibility and fog-light conditions. Cumulus clouds are dense, white fluffy clouds with a flat base, often resembling cotton balls, typically forming due to rising warm air in the atmosphere, generally stable but can grow vertically. Cumulonimbus clouds are a heavy and dense cloud of considerable vertical extent in the form of a mountain or huge tower, often associated with heavy precipitation, lightning, and thunder. The mature cumulonimbus cloud has a distinctive flat anvil-shaped top. They are towering, dark, thunderstorms, turbulence, and icing risks. Thunderstorms are among the most hazardous weather phenomena for aviation, producing turbulence, wind shear, lightning, hail, and rapid visibility changes that can compromise flight safety. So, moisture, instability, and lift are characteristics of what creates a thunderstorm. Moisture fuels cloud and precipitation development. Instability, warm air rising through cooler layers, and lift trigger mechanisms like fronts, terrain, and surface heating. The first stage of development is the cumulus stage. Updrafts dominate cloud builds vertically. The mature stage, precipitation begins, strongest winds, lightning, and turbulence. Dissipating stage has downdrafts that dominate. The storm weakens, but hazards still persist. So the impact on flight for turbulence is violent up and down drafts and loss of control risk. Wind shear has sudden changes in wind speed and direction. It's dangerous during takeoff and landing. Lightning can disable avionics, cause structural damage. Hail damages aircraft's surfaces, especially propellers and rotors. Heavy rain reduces visibility, affects lift and engine performance. Microbursts are intense downdrafts and can cause rapid descent or stall. Any precipitation is bad for your drone. You don't want to fly it if it's even lightly raining. Icing is one of the most dangerous weather hazards in aviation, reducing lift, increasing drag, and compromising control surfaces and sensors. Even a thin layer can severely degrade performance. Ice forms when supercooled water droplets strike an aircraft and freeze on contact. Conditions typically occur in clouds or precipitation at temperatures between -4 degrees Fahrenheit and 32 degrees Fahrenheit. The surfaces affected are wings, propellers, rotors, antennas, sensors, vents, and control surfaces. Flight hazards, lift reduction, even coarse frost can reduce lift by up to 30%. No? Okay, let's see. Fog is a low-lying cloud made of tiny water droplets that forms near the ground when air temperature matches the dew point. It drastically reduces your visibility. It's a serious hazard in aviation, especially during takeoff and landing. There are different types of fog. There's radiation fog, advection fog, slope fog, precipitation fog, and steam fog, or evaporation fog. Radiation fog is when the ground cools after sunset or a calm, clear night. Advection fog is when warm, moist air moves over a cooler surface. Upslope fog is moist air lifted by terrain cooling. Precipitation fog is when rain falls into a cooler air, evaporates, and saturates the air near the surface. Steam fog is cold air moves over warm water. Water evaporates and saturates the cold air. Density altitude is a critical concept in aviation. It tells you how your aircraft will perform based on air density, which changes with altitude, temperature, and humidity. The altitude at which the air density matches standard atmospheric conditions is the definition of density altitude. It's a performance metric, not a physical height. So the formula for this is pressure altitude corrected for non-standard temperature. Factors that increase density altitude. High temperature, warm air equals low density equals higher density altitude. Low pressure, less air equals higher density altitude. High humidity, moist air equals lighter equals higher density altitude. Impacts on flight. Reduced lift. Thinner air means wings and rotors generate less lift. Longer takeoff roll. Aircraft need more runway to get airborne. Poor climb performance. Slower ascent, especially in mountainous terrain. Drone relevance. Reduced thrust, shorter battery life, and sensor drift. Weather briefing. Weather briefing is a structured review of current and forecasted weather conditions along with your planned route of flight. The purpose is to identify hazards like low visibility, turbulence, icing, or convective activity before launch. It's required for all manned flights under FAA rules, strongly recommended for drone operations, especially beyond visual line of sight or near controlled airspace. The key elements of a briefing: METARs, current surface observations, wind, visibility, clouds, temperature, altimeter, and the TAF's terminal aerodrome forecasts, short-term forecasts for major airports. Then NOTAMs, notices to air emissions, temporary flight restrictions, and hazards. Weather reports, forecasts, and charts are standardized tools used to assess current and future atmospheric conditions. They help operators make informed decisions about flight safety, route planning, and launching time. Automated weather observing system is a fully automated system that continuously collects and broadcasts real-time weather data at airports and remote sites. The purpose is it provides pilots and drone operators with up-to-the-minute surface observations, especially useful for pre-flight briefings and in-flight updates. And what that gives you is your wind speed and direction, temperature dew point, altimeter setting, visibility, cloud height, precipitation. In your METARs, you will get a type of report, the station identifier, date and time of report, modifier, wind, visibility, weather, sky condition, temperature and dew point, altimeter setting, Zulu time, and any remarks that are going to be crucial for your flight. The METAR is an observation of current surface weather reported in a standard international format. METARs are issued on a regularly scheduled basis unless significant weather changes have occurred. A special METAR, SPECI, can be issued at any time between routine METAR reports. Your book gives you examples of what a METAR looks like. So let's break that down. A typical METAR report contains the following information in sequential order. Type of report. There are two types of METAR reports. The first is the routine METAR report that is transmitted on a regular time interval. The second is the aviation selected SPECI. This is a special report that can be given at any time to update the METAR for rapidly changing weather conditions, aircraft mishaps, or other critical information. Next, you have your station identifier, a 4-letter code as established by the International Civil Aviation Organization. In the 48 contiguous states, a unique 3-letter identifier is preceded by the letter K. For example, Gregg County Airport in Longview, Texas is identified by the letters KGGG. K being the country designated and GGG being the airport identifier. In other regions of the world, including Alaska and Hawaii, the first 2 letters of the 4 letters ICAO identifier indicate the region, country, or state. Alaska identifiers always begin with the letters PA, and Hawaii identifiers always begin with the letters PH. Notice, like in science, like biologists come up with these really complicated words, and geologists really long, complicated words. But in physical science, they have words like Big Bang or spaghettification. It's funny. Next, you'll have your date and time of report depicted in a 6-digit group. The first 2 digits are the date. The last 4 digits are the time of the METAR or SPECI, which is always given in coordinated universal time. A Z is appended to the end of the time to denote the time is given in Zulu time, as opposed to local time. Next is your modifier. It denotes the METAR came from an automated source where the report was corrected. If the notation auto is listed in the METAR, the report came from an automated source. It also lists A01 for no precipitation discriminator, or A02 with precipitation discriminator in the remarks section to indicate the type of precipitation sensors employed at the automated station. When the modifier COR is used, it identifies a corrected report sent out to replace an earlier report that contained an error. Next, you will have wind, reported with 5 digits, unless the speed is greater than 99 knots, in which case the wind is reported with 6 digits. The first 3 digits indicate the direction the true wind is blowing from in tens of degrees. If the wind is variable, it is reported as VRB. The last 2 digits indicate the speed of the wind in knots, unless the wind is greater than 99 knots, in which case it's indicated by 3 digits. If the winds are gusting, the letter G follows the wind speed. After the letter G, the peak gust recorded is provided. If the wind direction varies more than 60 degrees and the wind speed is greater than 6 knots, a separate group of numbers separated by a V will indicate the extremes of the wind directions. Next, you have visibility. The prevailing visibility is reported in statute miles as denoted by the letters SM. It is reported in both miles and fractions of miles. At times, runway's visual range, RVR, is reported following the prevailing visibility. RVR is the distance a pilot can see down the runway in a moving aircraft. When RVR is reported, it is shown with an R and the runway number followed by a slant, then the visual range in feet. For example, when the RVR is reported as R17L 1400 feet, it translates to a visual range of 1400 feet on runway 17 left. Next, you have weather. Can be broken down into 2 different categories: qualifiers and weather phenomena. First, the qualifiers of intensity, proximity, and the descriptor of the weather are given. Intensity may be light, moderate, or heavy. Proximity only depicts weather phenomena that are in the airport vicinity. The notation VC indicates a specific weather phenomena and is in the vicinity of 5 to 10 miles from the airport. Descriptors are used to describe certain types of precipitation and obscurations. Weather phenomena may be reported as being precipitation, obscurations, and other phenomena such as squalls or funnel clouds. Descriptions of weather phenomena as they begin or end and hailstone sizes are also listed in the remarks section. Figure 3.5 in your book, and it will show you the qualifiers and weather phenomena in the descriptors. Next, they list the sky condition, always reported in the sequence of amount, height, and type of indefinite ceiling height. The heights of the cloud bases are reported with a 3-digit number in hundreds of feet above. Next, you have sky condition, always reported in the sequence of amount, height, and type of indefinite ceiling height. The heights of the cloud bases are reported with a 3-digit number in hundreds of feet AGL. Clouds above 12,000 feet are not detected or reported by an automated station. The types of clouds, specifically towering cumulus clouds or cumulonimbus clouds, are reported with their height. Contractions are used to describe the amount of cloud coverage and obscuring phenomena. The amount of sky coverage is reported in 1/8 of the sky from horizon to horizon. Next is going to be your temperature and dew point listed. The air temperature and the dew point are always given in degrees Celsius. Temperatures below 0 Celsius are preceded by letter M to indicate minus. Next, list your altimeter setting, reported in inches of mercury. In a 4-digit number group, it is always preceded by the letter A. Rising or falling pressure may also be denoted in the remarks section as PRECRR or PRESFR. Zulu time is a term used in aviation for UTC, which places the entire world on one standard time. And finally, at the end of all these long numbers, you will have your remarks. It's a section always begins with the letters RMK. Comments may or may not appear in the section of the METAR. The information contained in the section may include wind data, variable visibility, beginning and end times of a particular phenomenon, pressure information, and various other information deemed necessary.